Good afternoon, class. I would like to get started. Okay, so last week we began our discussion of electromagnetic waves, which kind of loosely could be described as light. We tend to think of light as just the stuff that our eyeballs are sensitive to, but there's actually a whole spectrum called the electromagnetic spectrum of things a lot like light, but our eyeballs just aren't sensitive to them. And so here's a picture of an electromagnetic wave. It's just a wave that moves through space at the speed of light, and it's a self-sustaining wave of electricity and magnetism. And so when I get one of these guys moving through space, it'll go forever at the speed of light. Maybe just trivially, not really for our class. The reason it goes forever, it doesn't know time, but we're not going to get into that. There's no time if you're going the speed of light. Okay, so as I said, these things called photons, electromagnetic radiation, can exist in a whole range of frequencies and wavelengths. So as I've also said, that's really the only difference. They're massless, they're sizeless, they all go the same speed, they don't taste at all, they don't have colors. The only thing differentiating a microwave from a radio wave from something visible is their frequency and wavelength. And frequency goes up, wavelength goes down. The product of those two numbers, frequency and wavelength, is c, the speed of light, 300 million meters per second. Okay, so we've, why not? We've just kind of started from the left and just started moving forward. So we did start talking about radio waves. The longer radio waves are AM radio waves. So if you look at the side there, AM radio waves, if you imagine your car, you tune in to AM 1060 or whatever, and you can imagine your car antenna. Cars these days don't have that type of antenna much anymore. Most of the time, your car antenna is embedded in the window or embedded in the structure of the car. But back in the day, you used to have this like metal thing sticking out of your car, and you can imagine radio waves passing by. Those, if you're tuned into an AM station, those radio waves are actually kilometers long. So imagine something like the size of, I don't know, a kilometer, like the size of Charlottesville, just going past your radio. They're very, very large. So if we start on the far left, we're talking about AM radio waves, amplitude modulated radio waves. A little smaller than that is FM radio waves. We've talked about that. We keep going, we get into the microwave spectrum, and that's no microwave today, so I'm sorry, we won't be frying anything. We'll try to do something as exciting as frying CDs, but that was probably the apex of the semester right there, cooking a CD. We did talk about microwaves. Microwaves are just radio waves that are a little bit smaller in frequency. The microwaves we're most familiar with are the things that cook our food and the things our cell phones use to communicate, and our Wi-Fi routers, which are all right about the same place, which, as I said, should be slightly disconcerting. The reassurance is the intensity or the amount of energy coming out of your microwave is greater. So yes, it's the same stuff, but you can have a little comfort in knowing that it's not as energetic. There's not as many coming out of your cell phone, but it's the same stuff. And that stuff is used not to, they're actually low energy waves. So if you go to the left, as you go to the left on this chart, this is lower and lower energy. So if you were going to be really scared, I said this last class, if you're going to be scared of microwaves, you should also be scared of red light and rainbows and the light bulbs in this classroom and stuff like that. So it's not their energy that's dangerous. As you go much past purple, that is dangerous stuff. So you don't ever want to get hit by ultraviolet or X-rays or gamma rays. That's always going to have enough energy to do damage. When you're over on the left side of past infrared, what's damaging is the fact that you and I are made of mostly water. And if I send microwaves into my brain like this, the microwaves coming out of my phone, I don't even have to have a phone conversation going on. My phone is constantly checking for text messages, talking to the cell phone tower, seeing what time it is, checking its GPS location. So my phone is always emitting things. And if I hold it up to my brain long enough, I can jiggle the polar water molecules in my brain. And so we talked about that last class, that the way microwaves work is they, using electromagnetic fields, jiggle polar molecules like the water in your blood, in your brain, in your chicken, in your coffee, in your cheese, or your Hot Pocket, whatever. Caitlin, question? That's an excellent question. The question is, wouldn't always do that. And that's actually true, that that wave right there is a wave of electric field going up and down. That's the important part, is the red one. And if I send an FM radio wave through your head right now, which is actually happening right now in this room, I doubt we're shielded from cell phone signals and radio waves. So right now, FM radio is passing through your body. AM radio is passing through your body. Every cell phone signal in this room right now is passing through your body. The cell tower doesn't know where your phone is and your neighbor's phone is. So the cell phone tower is just blasting everyone's phone conversations at you all day long. So if you think about it, when you're outside or even in this room right now, you are just awash in everybody's phone conversation, and every text message, every router, and all that. Here's the one, and every radio channel. So everything on the FM dial and AM dial is in this room right now, and it's going through you and jiggling you. The main difference is because of the wavelength and frequency, how it will interact with matter changes. And so radio waves right now are so long, they barely have time to get one of my water molecules going before it's off. And so it's very slow. And very fast, I'm actually opaque to a good chunk of the spectrum. And so green light just bounces off me, never makes it to my brain. And so I'm either not that sensitive or opaque to most of that picture. So the ones that microwaves are, and the reason we use microwaves, the reason we use them for communication and for cooking food is mainly because they will interact with, well, the reason we use them for cooking food is they will go into your food and interact with that matter. And the reason we use them for communication is the sealing is opaque to it. So when you're thinking about the properties of all these different types of waves, the way they interact with matter is very frequency dependent. So yes, any one of those waves will jiggle a polar molecule. The way it interacts with the rest of the story is very frequency dependent. And so yeah, like I said, I'm opaque to most of that. So my brain is not getting warmed by the green light in this room right now because I'm reflecting most of the green light in this room right now. Now, if there was X-rays or gamma rays in this room, those actually would go into my body and probably cause damage. That's why you don't want that. Those are very energetic. Okay, so that's cooking food. Before we leave the microwave end of the spectrum, right as we get right out of the microwave, we're almost to infrared, which is where I want to get to next. I want to talk about one more type of microwave. So the microwaves we've talked about so far for cell phones and Wi-Fi and microwaving your food is a pretty narrow part of the microwave spectrum. That's 2.4 gigahertz. That's about a 12 centimeter wave. Microwave is a kind of a broad term. You can see up there 10 to the negative 2. That's a centimeter, so it's like that. Microwaves are kind of broad term, and microwave also encompasses another set of photons. One of my favorite sets of photons. It's these photons, and it's also one of my favorite physics stories that I think in the mid 60s, two guys, Penzias and Wilson, they were. I'm going to say some things that I think are, if I remember the details right, I think they were working for Bell Labs. I think they were in New Jersey somewhere. Those are just maybe true. They were out there measuring radio waves. So they built this big device, this big telescope basically. And I've said, I think last class, what a telescope is just a big eyeball that focuses light into your eyeball. It's just a big lens that just focuses visible light. And if you're going to look into space, and you want to know what's out there, it's probably a good idea to think about more than just the little bit of the spectrum that our eyeballs are sensitive to. There's a whole lot else out there worth looking at. And so these guys built what's called a radio telescope. They built it looked like a big megaphone or something that you would use to listen to something far away, but it was meant to reflect and capture and measure radio waves. So Penzias and Wilson, 1960 something, got their big radio telescope out, and they're out there trying to make measurements. And what they're trying to measure is very faint, so they had to have no external noise in their signal. They had to have a really good, clean signal. And so they get out there and they build this big telescope and they get their experiment ready and they turn it on, and before they even point it to any source of signal, they just hear a buzz, a static in their signal. And so there's no source. They're just pointing at a blank spot of sky, so they're not supposed to be getting anything yet, but they're just getting a signal. And so they think, okay, there's, buzzes in your signal are like one of the most common things in electronics, and any kind of, when you're doing an experiment, that's super common. You're like, oh shoot, I gotta tighten that wire, or I gotta get rid of that old crappy USB cable or something. Buzzes are pretty common. So they think, okay, we've got a source of noise. They go through every possible option to get rid of this noise. They go in there and they clean out their device, and they just make sure everything is totally fine. They make sure they're pointed at a totally blank spot of sky, and they keep getting this noise. And around that time of in the history of physics, we were also coming up with this idea that there was a Big Bang, and there was a beginning of the universe, and what that looked like. And it turns out what Penzias and Wilson totally did not mean to do, what they were actually doing is they were picking up the signals from the Big Bang. So our universe, as far as we know, began 14.7 billion years ago. And you can imagine to go from a kind of nothing into the universe was a pretty big event, pretty cataclysmic event. It was a pretty violent event. And it was so hot at the beginning of the universe that it took about 300 or 400 million years for the universe to even cool down enough that we could have atoms. And so the universe spent its first 300 or 400 million years just so hot there couldn't even be atoms. But once the universe kind of cooled enough that we started to get protons and electrons that were already existing, but they existed in this plasma. Once protons and electrons got together and made hydrogen, the stuff that eventually made stars and eventually made us, once they were able to get together and make hydrogen about 300 million years after the beginning of the universe, all of a sudden these photons that were bound up in that plasma were free to roam the universe. That was about 14 billion years ago. Those photons still exist today. Those photons from the very beginning of our universe still exist, and they are still traveling throughout the universe. So in fact, if you ever turn your TV on and you get a static signal, just that snow that's on and it's hard to get nowadays because most TVs just have a digital cable signal or something. But I'm sure, hopefully we're all familiar with snow that just on the front of your TV. Some of that signal is actually the Big Bang. Some of that signal, when you turn on TV to get some snow, some of that is actually photons that have been traveling through the universe since the beginning of the universe. And so when Penzias and Wilson pointed their telescope at the sky, it was the first time someone had built a telescope that sensitive and had pointed it at just a blank piece of sky. They started receiving signals. They started receiving photons. But there weren't supposed to be, there was no source of photons. And it took them a while to believe, and it was controversial for a long time, it took them a while for them to believe that this is actually what they were getting. They were getting what's now called the cosmic microwave background radiation. That's a mouthful, but it makes sense. Cosmic, that's us, our cosmos. Cosmic microwave, it turned out it was in the microwave part of the spectrum. So here's what happened. Not to get too much into Big Bang cosmology, but when the universe began, it was very small. And those photons were very, very energetic, probably way over in the gamma side of things. Take a gamma ray in a very small universe and stretch that universe out, and those waves got stretched out. And so when we point a telescope out into the sky now, when we get one of those photons, which are waves in space, right? That's what we've talked about. A photon is a wave in space itself. Those photons have been stretched out because space itself has stretched out. The universe is expanding, and the universe itself is stretching. And all the photons in the universe are stretching as the universe expands. And so when we point our telescope into the sky and we get one of these photons, it's in the microwave part of the spectrum. And so it's the cosmic microwave background radiation. It's a background because it's everywhere. All these photons, they fill the entire universe because they were there since the universe began. So what you're looking at is a map. If you were to take a telescope or a microwave-oscope or whatever and point it all around and look, you could map out the sky. That's the sky as if you were inside a sphere. So if I look there and look there and look there and look there and look there, I see microwaves coming from every different direction. And we've mapped them, and that's a map of them right there. They all, well, we're going to get in this a little bit today. Actually, that's kind of our next thing, so that might be a segue in a second. But yeah, they're all around, they all indicate a temperature. And we'll talk about that in a second, what that means. But they all indicate a temperature of around 2 or 3 degrees Kelvin, and that's why that picture is not uniform. It's not just all blue or all green or something like that. There's variations. And one of the cooler things about this discovery, so Penzias and Wilson in the 60s discovered this. Since then, we've made a pretty good map of it. We've looked and seen where we see photons coming from. And this map has variations in it. We can actually map those variations to structures that exist in the universe today. And so we can see that the sometimes this is called the universe's baby picture. This is like the first time light existed in the universe, and we can see it today, which is crazy. And so I don't know how much we'll talk about this semester, but one of my favorite things about cosmology is when you look at anything, you're looking back in time. I'm not seeing you as you are right now. I'm seeing you as you were, let's see, that's about 15 nanoseconds ago. And the people in the back, I'm seeing as they were 100 nanoseconds ago. I can't see you. I'm always looking into the past. So right now, you're not seeing me. You're seeing me when I was younger. It's a fact. It's just that you can't see people at the same time, right? It takes a while for things to get there. And so when we look at the sun, you're not seeing the sun. The sun could not be there. Like you could go outside, look at the sun. It looks like it's there. It's possible it's gone. You don't know it because it takes 8 minutes for the light to get here. And so the sun could, I don't know, somebody could come and steal the sun, and you wouldn't know it for 8 minutes. And so the further you look, in the sky, you're looking back. You look at the sun, you're looking 8 minutes ago. You look at the next farthest star, you're looking years ago. You look at a lot of stars, you're looking thousands of years ago, millions of years ago, billions of years ago. Well, we can only go back so far. This is about as far as back as we can go. This is the universe's baby picture. It's about 14 billion years old. Yeah. Radiation. Yeah. Cosmic microwave background radiation. And so that's kind of the first photons that existed, and we can point our telescopes and see them still today, which I think is pretty cool. And yeah, like I said, it's also cool that we can see, so that's what the universe looked like about 14 billion years ago. And you could look at my baby picture and kind of see what I was going to look like later. The universe is the same way. Those irregularities point to structures that exist 14 billion years later today. That we can sort of map them forward. Okay. That's a nice segue to the next very important thing we have to talk about today. And that is, when I see photons coming from the cosmic microwave background radiation, those are indicative of a temperature. And in fact, all light can be indicative of a temperature. Here's what I mean by that. So when physicists look at that picture, they say, wow, the photons I'm getting are indicative of something around 2 or 3 degrees above absolute zero. I can read the temperature of that light. And the reason I can do that is because all things emit photons. You and I are emitting photons right now. You and I are like little light bulbs. And the photons I'm emitting are very characteristic of my temperature. And so the physics term for that is blackbody radiation, and here's why we call it blackbody radiation. If you're seeing me right now, it's not because I'm glowing. I'm not emitting, well, I am glowing. I'm not glowing in a frequency you can detect with your eyeballs. If you can see me right now, it's because I'm reflecting light. I'm reflecting some blue and some gray light. It's no such thing as gray light. But I'm reflecting some blue and some pink hues, I guess. So, but I am actually emitting light. And so if you wanted to just read the frequencies I'm emitting, you'd have to cover me with a matte black, something that is not reflective at all. So you can imagine if you go to a theater or something, a lot of things are covered in matte black because you don't want to see them. If you want to see something, it's just make it a non-reflective surface. A non-reflective surface, it just appears black. So something called blackbody radiation, if I am seeing it, it's coming solely from its temperature. It's not reflecting any light. And yeah, a real blackbody emitter doesn't exist, but we can come kind of close. So let's look at an example of that. So let me pull up my camera here. Okay, what am I looking at right now? Am I looking at somebody? What is that even? I think I'm looking at somebody's shoes or something. What is that? Okay. All right. Well, anyway, what you're seeing right now is this camera. And so if I'm going to point it, I don't know, I'll point it over at the door. So there's the door. And so what this camera is doing, this camera is just giving us a picture into a world that we tend to just forget exists. And that is, and I'm trying to emphasize this a lot these last couple classes, is that we have these things called eyeballs that give us a picture of what is around us. And it is, actually, if I could, in my top 10 things that I think a good physicist mindset, here's one of the top 10 things of a good physicist mindset, is the knowledge that the picture of the world that your senses are giving you is limited and biased. And so when I look at the world, well, first of all, if I want to look at the world and see anything that's not within arm's reach, so I can touch stuff within about a meter, I can hear stuff, but that's only has to be pretty loud. It has to be within a certain spectrum, so the human ear only responds like 20 hertz to 20,000 hertz. I can see stuff, but I can, and here's the lesson for the day, my visual sense is so narrow. It's just this tiny little sliver of the electromagnetic spectrum. And what else? I can smell stuff. That has to actually, something has to be emitting this smell and get to me. And what's the last one? No, is that all of them? Hearing, smelling, touch. Okay. Did I forget any? Okay. So I think that's all of them, right? 5, and then we think there might be a 6. Okay. But if all I have to do is take a camera that is just slightly sensitive to some of the light outside of that spectrum, and I can see the world slightly differently. So here's the classroom right now. The classroom, probably because you guys are in it, is kind of warm. Just outside the classroom is purple. That is colder outside. So because the lights are on in here and you guys are in here, this room is, let's see, point up here, is like 20-some degrees. And that guy's going under the light bulbs. So those light bulbs are about 27. Even though they're fluorescent, they're slightly warmer. So that's the temperature you're seeing. So the hallway's a little cooler. But then let's look at you guys. There, you guys are all like little light bulbs. That's what I keep saying. You guys are little light bulbs. People in the back are cold, I guess. So you guys are emitting let's see. Someone's trying to wave. Are we getting anyone? There it is. There's a delay. There's a hand. Okay. So you guys are all emitting light. It's just barely outside of the visible spectrum. It's not even some crazy type of light. It's the light that these light bulbs are making just a little bit infrared. So you guys are emitting light right now. I mean, and light is just, yeah, if I want to turn on a light bulb, all I'm doing is getting something really hot, and so it emits light in the visible. You guys are all about body temperature. By definition, you're emitting light. So let's see, here's my hand. My hand is relatively warm. And so I can take my fingers and I can make friction. Let's see. And I can make, you can see that where my thumb and my forefinger were touching, I can make it a little bit hotter. And so right there on my hand, you see that on my finger is kind of white. And as you watch it for a second, it'll slowly cool off as that gives up temperature to the environment. And actually, that little cursor you're seeing is finding the hottest spot. And so if I rub my fingers enough, that becomes the hottest spot, my thumb. But then because my thumb is on the extremity, it eventually cools off, and then that little cursor is going to go find something hotter eventually, like somewhere on my palm. Yeah. Okay. So what you're seeing is a picture very similar to what our eyeballs are seeing. Let's go back here. It's a picture just very similar to what your eyeballs are seeing. It's just in a slightly different part of the spectrum. So your eyeballs are sensitive to what we call the visible part of the spectrum, and there's the wavelength between like 400 and 700 nanometers. Maybe we don't need to know that. And once you just get slightly beyond red, or just slightly short of red, infrared, that's the stuff you and I are emitting right now. Okay. And so, yeah, it's important to know that all things above absolute zero, in other words, all things, are emitting photons. Everything is emitting photons. Right now, that light bulb right there, let's go back to my picture. See, I've got a light bulb at the front of the room. Right now, that light bulb in this camera looks pretty bright. Notice it's almost indistinguishable from the lights above the chalkboard. So this light bulb in the front of the room is emitting light, but it's just mostly in a part of the spectrum you and I are not sensitive to. And so if I zoom in on it, so I can turn that on. And I can actually measure the temperature of it. You can see that right now it's about 140 up in the top left. You can see it's about 140 degrees Celsius. That's pretty hot. And the color of that light, right now most of us would call that kind of white. Now it's maybe kind of orangish yellow. The color of that is completely temperature dependent. And so right now I've turned down the voltage, which is turning down the temperature, which is turning down the color. And so that color that's now sort of orangish, and I can make it even colder, and it's going to be sort of a orangish red. So a light bulb is actually not a bad black body emitter, meaning the light you're seeing is completely dependent on how hot it is. And I may have mentioned before that this is an incandescent bulb, and incandescent bulbs use a pretty old school idea. And that is, here's the idea that incandescent bulbs are based on. We humans are used to seeing light coming from a sun that is about 5,800 degrees Kelvin. The surface of our, oh, that was the eye clicker, I just gave it away. Oh well. The surface of our sun is about 5,800 degrees Kelvin. And that's what our eyeballs are used to seeing. So here's what Thomas Edison and his buddies said. Well, if we want to make an artificial source of that, we just have to get something up to about 5,800 degrees Kelvin. That's what an incandescent bulb is doing. If I want to make something that looks kind of like a little sun, here's what I do. I just have to heat something up to 5,800 degrees Kelvin. Because here's the moral of the story that I keep trying to get to, and that is everything emits photons. Everything emits photons in this curve. And where you max out on that curve, in other words, where the peak of that curve is, depends on how hot you are. So you and I, right now, are like little light bulbs, and at the peak of our curve is in the infrared. That doesn't mean you're not emitting any visible light. It's just very, 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 very small. So you actually are probably emitting some photons in the visible part of the spectrum, just not perceivable. But because you're at about body temperature, where your curve peaks out is not in the visible part of the spectrum. So that rainbow there in the middle, that's the visible part of the spectrum. And so all I have to do to make something visible is get it hot enough. Get it hot enough where its peak starts moving over into the visible. And so this light bulb right now is emitting light. It's just not perceivable to we humans. All I have to do is literally just make it hotter. That's what's happening in that filament right now. It's just getting hotter. And so that's what's happening in the sun. That's why the sun emits visible light. That's why if you ever turn a stove on, the old kind of stove with a coil, turn on high and wait a second, it slowly glows dark red, and then you wait a little longer and it gets a little bit brighter red than orange. That is because it's getting hotter, and as it gets hotter, its curve, you can see 3 representative curves here, is just moving over into the visible part of the spectrum. Okay. Any questions? Yes. Oh yeah, this is the question was that's what is that chart called? That's a really nice chart to have kind of in your head, and that's a black body curve or a black body spectrum. And again, because when I see blue, it might be just because the thing is blue. And so that's the reason we call it a black body curve, is that I don't want to be confused by the fact that it's blue. I want to make something that the only reason I'm seeing any light is because of the temperature. And that's why those coil stoves are a pretty good example. Those coil stoves are sort of a matte black. And so when they start glowing red, it's not because you've painted them red. It's because the photons coming off of it are being emitted due to the heat. And so that's a black body curve or black body spectrum. Yeah. And so take something, anything, just get it hot enough, it'll start glowing. And it'll start glowing that characteristic curve. And so that's why everything, when you start heating it up, everything starts glowing red, because that's the furthest to the right. And this is kind of backwards to the other chart I've had up there, so don't let that confuse you. But on this chart, the red is the furthest to the right. And as these curves start, hopefully everyone can see these, the little curve on the bottom is 4,500 degrees Kelvin. That would be something a little colder than the sun. That would be like that light bulb or your stove when it's not that hot. And as you start moving over, you just start emitting more orange, then more yellow, then more green, and then more blue, more purple, etc. Yeah. Yeah, great question. So if you've ever managed to make a blue flame, you can do that if you're careful with just wood fire. But wood fires tend to not get, I mean, we're talking like that one's 7,500 degrees Kelvin. There's other things that glow hotter, or like in the center of a candle maybe or something. But yeah, if you're seeing something starts looking kind of bluish, it's moved far enough over that there's less red. So if you look at that top curve has a lot of blue and purple in it, some red, but it's kind of moving over into the blue. And I think you might be able to see from that curve why there are no such thing as green stars. If I were to make something glow hot enough that it maxed out in the green. In fact, that's a nice little bit of trivia. 6,000 degrees Kelvin, that's basically our sun. Our sun, if you were to ask anybody, what color is the sun? Most people would say yellow or white. That's only because, that's I think where we need to go next, probably for the rest of class, is talking about how humans make up color, basically. Our sun is basically green. Our sun maxes out in the green. We humans call it white or yellowish, but really, our sun is the most photons our sun puts out is in the green. But the way we humans perceive color, which is maybe where we need to go next, is if we see a lot of green, and notice if you look at that curve, a green star, that's the middle curve, 6,000 degrees Kelvin. A green star is putting out a lot of green, mostly green, but a lot of yellow, a lot of orange, a lot of red, and a lot of blue, and a lot of purple. And maybe we know from like elementary school art class or something, if I see all the colors together, my brain just says that's white. And so when I look up at the sun, which you shouldn't do, and say, oh, that's white, or if you look at anything that's white, this is white, it's not. That's made up. It's just you're getting an equal measure of all the colors, and your brain calls that white. In fact, here's the thing maybe you should fall asleep thinking about tonight. That is, there is no such thing as color. Maybe take a second and try to picture this room right now, and imagine a creature to walk into this room that didn't have this brain. Our brain makes up color. There's no such thing as red. There's no such thing as yellow. There's no such thing as blue. It's just a perception. And so imagine a creature that didn't have that perception just walks in this room right now. Really, all we are, all of us are wearing cotton mesh, and we're sitting in a cotton mesh seat. And so you could imagine if my eyeballs did not, it's not even eyeballs, it's the brain. If my brain did not go, oh, that's a blue or that's a photon of a 400 nanometer wavelength. I'm going to call that blue. I'm going to perceive that as blue. And oh, that's a photon in a 700 nanometer wavelength. I'm going to call that red. If my brain didn't do that, maybe it's not even a creature. Maybe it's just a human that's evolved past perceiving color. I don't know. We could just all be gray blobs, or imagine imagine this room right now where there's no such thing as color. We're all monochrome gray. That is actually a closer picture to what is in this room right now. It's a bunch of monochrome. We're all just covered in cotton. We're all just the same thing pretty much. And there's walls and human flesh and hair. That's all that's in this room right now. And that's all, the color of it is totally manufactured. It's all a perception thing. And so here's what the human eye does, and this might take us the rest of class. I'll have to do the eye clicker at some point. Let's see. I lost my eye clicker. There it is. Just so I know everyone's here, let's do an eye clicker right now. Okay. I think we'll take 30 seconds to vote on this one because I think I gave it away. Here's the test. Was people listening? Yep. So far, people were listening. Okay. Uh-oh. Not working? I'm getting 170. No, I'm only getting 25 people. Uh-oh. No waves. I'm not. No bass. This guy. 2 computer. Let's try that. Bonk. All right, I'm going to try that again. Are we in there? Okay. Somebody unplugged me. So right now, as you guys are because everyone knows to click B, you don't have to listen. You don't have to be thinking right now. Right now, everyone's pushing a button that is causing a little oscillation and a little antenna inside there to send out electromagnetic blast with your unique ID. And this little antenna right here is being oscillated at the same frequency and is picking up that electromagnetic wave being blasted from your iClicker and decoding it. And the crazy thing is, I mean, there's 188 people in this class right now, and not only am I able to get electromagnetic signals, which is awesome by itself, it's able to decode whose signals were whose, which I think is also pretty impressive. So that, yeah, there's your PSA for the day. Don't sleep with your phone and don't sleep with your iClicker. I know some people might be tempted to do that. Take 20 more seconds. 9 of us are just determined that I'm wrong and it is not B. All right. Okay, thanks. There we go. And that's good. Okay. Yes. The sun, the surface of the sun is about 6,000 degrees Kelvin. And here's a nice little picture of that. That gray line, that's the blackbody curve for something that is 5250 in this case. Then our sun, if you were to measure all the wavelengths at the top of our atmosphere, you would get a blackbody spectrum. You would get that nice curve. And you would be getting some light in the UV, you'd be getting some light in the infrared, you would be getting X-rays, you'd be getting gamma rays, all the above. You would be getting most of the light in the visible, which we've talked about. And a nice thing about this little chart is it shows you that yellow curve is what's actually at the surface, what gets to the top of our atmosphere. Fortunately for us, our Earth is coated in an atmosphere that blocks out a lot of that. And so you can see these little windows in our atmosphere. So there's little windows, little gaps in the atmosphere that allow certain of those frequencies, like light, fortunately, to get to us. But a lot of it gets blocked out. And you can even see that ozone, O3, blocks out some, water blocks out some, CO2 blocks out some. And so what makes it to the top of the atmosphere is not necessarily what makes it down here. And by the way, yeah, so we've talked a little bit about how the wavelength of certain photons determines how it's going to interact with matter. And that's a pretty good picture of that. So some of the photons just go right through the clouds, some bounce off the clouds. That's why greenhouse gases are bad, because we trap in thermal radiation. That's why a certain part of our atmosphere is nice. We can actually bounce radio waves off of it. So if I want to talk to China, I don't need a line of sight. I can actually bounce radio waves off of the atmosphere because the atmosphere is reflective to certain frequencies. Okay, let's talk a little bit about a couple more things about stars, and we might start talking about human perception of light. So I already mentioned this. You're not going to see any green stars because by the time you get to a green star, you're also seeing a lot of blue and red and yellow, and so humans are going to call that white. And so if you look at this spectrum here, you can see that some stars, the colder stars, that one on the left is 2,500 degrees, the colder stars are maxing out actually just in the barely visible part of the spectrum. So a colder star is emitting a lot of infrared light like you and I are doing right now, but also is hot enough that it's emitting some in the red, but just a little in the blue. Our star maxes out right in the middle part of the spectrum, And as you get hotter and hotter, there's an 18,000 degree star. That star is maxing out in the ultraviolet. Most of what it's putting out is UV light. But because this is a continuous curve, you're always going to get some red and some blue and some visible. But it's just where it maxes out sort of depends on how we're going to perceive it. So that star on the right there, you can see it's maxed out in the ultraviolet, but it's still getting a fair amount of purple and blue, and it's going to look kind of bluish. Okay. Question? Yep. Good question. It's about white hot. Yeah, so white hot is the surface of the sun, and you can get a lot hotter than that. So white hot is very hot. So it's hot for a fire. It's cold for a star. So it kind of depends. Yeah. Let's see. We have 3 minutes left. Let's start talking about how humans perceive this stuff. So as I said, there's a tiny little sliver in the middle called the visible part of the spectrum. And there's even a tinier sliver than that our eyeballs are sensitive to. You've probably heard of rods and cones. That we have these things called eyeballs, and in the back is a thing called a retina. I think that's hopefully common knowledge for a UVA student. That the retina has things in the back called rods and cones. The cones are cells. I mean, if you're going to perceive these things called photons, there has to be a mechanism that the eyeball gets them and the brain perceives them. Here's the mechanism. A photon is a little packet of energy. I think I've said that before. That little packet of energy goes through a little 1/8 inch hole called a pupil and smacks you in the back of the eyeball. When that happens, that little packet of energy can kick off a chemical reaction. And your eyeball is coated with these cone cells that are waiting for a little chemical reaction to occur. And there's basically a little energy barrier just waiting for a little photon to hit them. And it's just really sensitive to 3 types. So of all of the infinite spectrum of colors in the universe, really we are just sensitive to 3. We're sensitive to red, green, and blue. Humans can only perceive red, green, and blue. We have 3 types of cells, red, green, and blue. If you've ever seen anything that is not red, green, or blue, that's your brain making it up. So if you've ever seen purple, that's your brain getting hit by a red photon and a blue photon and going, or getting hit by a purple photon, but then having its red and blue sensors kicked off in equal portions and your brain going, that's purple. If you've ever seen yellow, you got hit by a yellow photon, but notice you don't have a yellow sensor. So if your red and your green get kicked off in equal amounts, your brain goes, oh, I'm going to call that yellow. And so really you only have 3 sensors in the back, and your brain is just picking up, oh, that's a little bluish, that's a little reddish, I'm going to call that purple, I'm going to call that yellow. But every color you've ever perceived, other than just pure red, pure green, and pure blue, your brain is interpreting a signal and making up what to call that. And so if you're looking at something pink right now, that's just your brain going, okay, I'm going to call that thing that I'm getting, I'm going to call that pink. That is probably what we're going to have to pick up next class. See you Wednesday.